Hello everybody. I want to quickly make a short video just adding a little bit more to what we did at the end of class about free body diagrams. I realized I rushed through it and wanted to just take a couple minutes to introduce that to you a little less frenetically and a little more formally. So I have a bunch of situations here and I want us to think about what we talked about today. How forces are the agents of change in the universe, how they're what cause changes in an object's motion, how you can't have an acceleration without a force, but how you don't necessarily need a force to keep something moving. You only need it to cancel out other resistive forces, like in the case of pushing a box across the floor. So let's take a look at this and see what's going on and see if we can make sense of these. So I have a few situations here. The first one is a puck sliding on ice with negligible friction and air resistance. So one thing about free body diagrams, I was being a little loose in class about it, but the best way to do it is really to use a dot to represent the object and draw all the forces super clearly on the dot. So here's a puck sliding, negligible friction or air resistance. Now we know it got pushed to get going, right? Someone had to give it a hit with a hockey stick. But once it leaves the stick, you always have to ask yourself, and I find it helpful to even circle the object and say, what's touching it now? What's pulling on it now? So here's the object. The answer is nothing's pushing or pulling on it sideways. It has inertia, it has motion, but it doesn't have any forces acting on it horizontally. Therefore, it can't get faster or slower. It can just travel at a constant speed, we'll see. The forces acting down are its weight. The force acting up is the normal force. And that's it. And those two vectors should be equal because it's not accelerating up or down. It's an equilibrium both vertically and horizontally. There's no forces on it. Okay, pushing a box on a rough surface, but the box won't move. This is another good one because there's a bunch of forces on it, but they all happen to balance out. So here's the box. Well, we know the box has a weight, and we know the box has a normal force. Let's isolate the box, right? Now, we know there's a person pulling on it, which you can just draw as an arrow coming out of the front, even though the push is from the other side. When you squeeze it down to a particle, there is no front or back. So we can write force push. But if that were the force diagram, this box would accelerate forward because there's a net forward force. What this means, the fact that it's not moving, it must mean that friction, which I'm just going to write as a lowercase f, is acting opposite the push, and these two forces must be equal in order for it not to move. So the static friction resisting the motion is equal to the forward push. Here's a simple but somewhat tricky one. Similar to the hockey puck, it's a football flying through the air, but you're ignoring air resistance. So it's moving because somebody pushed it at some point. But right now, there's nothing touching it. There's no contact forces, and that's important. It has speed, it has inertia, but it does not have any forces that are contact forces. The only force acting on it is the field force of its weight, and that's why as it rises, it slows down. As it falls, it speeds up. There's no normal force in this case because it's not in contact with the ground. Okay, so if I were to really formalize that, I would do the force diagram as a dot with W. The dots are helpful. They really help you go through a level of abstraction that I think forces you to think really carefully. Okay, traffic light hanging by two cables. I like this one because if it can be rigorous and still relatively simple. So you have a traffic light, it's hanging down, and we know that the weight is touching it. Let's circle the traffic light. Right, we know weight's pulling down. Now there's two cables pushing up. If there were one cable, I'd draw an upwards force equaling length to the weight. But since there are two cables, I should have two tension forces, each half as long as the weight because they're each supporting half of the weight. Now you're pushing a box on a rough surface, so this was 4. Number 5, you're pushing a box on a rough surface and it accelerates. Rough surface means there's friction, but the fact that it's accelerating forward means that you must be pushing harder and overcoming the friction enough to allow it to pick up speed. So let's do that one. We know the weight and the normal force are equal and equal in length. And then we know there's the forward force of your push. And then the friction must be less because your push is causing it to accelerate. Now, you don't know the exact numbers, so you can't draw them exactly right, but this at least represents the idea. And then this last one, you're pulling a crate on a rough surface, so there's friction, and it's moving at a constant speed. Now what you really want to do here, since we're interested in the force diagram for the crate, is you want to isolate it because there is a person here and we could look at the forces on the person if we wanted to, but let's look at the crate and think what's touching it directly. Now the person's not touching it directly like they were in the other crate examples. What's happening here is the rope is touching it. So we have to be very specific. Here's our crate. We have the tension in the rope acting as the force that pulls it forward. We have the weight acting down and the normal force acting up. And now here's what's tricky. It's moving at a constant speed. If you were pulling harder than friction, it would pick up speed. If friction were pulling harder, it either wouldn't move or it would slow down. So what's the option? If you're moving at a constant speed, it must mean you got it going somehow. But the friction must be exactly equal to the tension so that you have no excess force in either direction. That's a hard concept which we'll continue to talk about, but I think if you think about it a little bit as the alternatives, what would happen if friction or tension were greater, neither one would be a constant speed kind of situation. The only thing that would satisfy constant speed is if they were equal. So I hope this was helpful. You could watch all or part of it, and I think it'll help you with tonight's assignment, but also be a good reference for the future. Okay, bye.